Okay, so this one reads that in a time of 10 seconds, a 70-kilogram student runs up 2 flights of stairs with a combined vertical height of 8 meters. Compute the student's average power output in doing work against gravity. Okay, and so we can start off with a little picture here. So there's my 2 flights of stairs. Here's our little student. Okay, and then what we're going to get is that to go from here to here is going to take, what did they say? 10 seconds? Yeah, 10 seconds. And we have that the mass of our student is, 70 kilograms. Okay, like so. And so then what we're going to look at is that we'll go in and start off with our how much work was done, by the student against gravity is the way that they phrase that. And so we're going to start off with our work energy theorem. So we're going to start off with the net work is the change in the kinetic energy. Okay. Now, the thing in the problem is that they didn't describe how the student sped up as they went up the stairs or that they slowed down as they went up the stairs. So the implication is that there was no change in kinetic energy. Because we can't just kind of come up with, oh, they, sped up by this amount or they slowed down by this amount as they ran up the stairs just out of the blue. So by not saying anything, we're stating that really the kinetic energy did not change. So either that it remains the same, both at the bottom and at the top, or a lot of times they might say going from rest to rest. But it wasn't explicit in the wording of the problem. But what we get is that this change in the kinetic energy is going to be 0. And then what we're going to look at is the way that this goes is that in order for the student to kind of, run up the stairs, then they're going to push down on the tread so that the tread pushes up on them. Okay, so when we look at the forces acting on our student, then we have our gravitational force. And then what we have is the normal force between their feet and the ground. Okay. And so the idea is that as they push down on the tread pushes up on them and up the stairs they go, right? I mean, because unless it's an escalator, then if they don't push down, then they don't go up kind of thing. So it's a reactive type of force. And so while the forces acting on here are going to be this normal and then the gravity, what you get is that it's this normal force is related to the effort done by the student in climbing the stairs. Because in order for them to push down, to have the floor push up for them to go up, then if they don't push down, they don't go up. Like I said, it's unless it's an escalator. And so then what happens is that we can take, so this is the work we want to use in determining the average power output of the student. This is the amount of work that we want to calculate. So the work done by the quote unquote normal force is minus the work done by gravity. And this is the language in the problem, the power output in doing work against gravity. So this work is the minus the work done by gravity. This is the work essentially exerted by the student, because the normal force in general will not cause you to climb stairs unless you're doing, additional downward pushing on the floor to make it go up. And so that's how we walk, is essentially that idea, is that, we push back on the floor so that the floor pushes forward on us so that we move forward. We don't push back, the floor doesn't push forward. Again, unless it's, the people movers in the airport or whatever, then yeah, that's the deal. Now, since the gravitational force is conservative, then what you get is that this is minus the change in our gravitational potential energy. So we get this minus a minus, which gives us a plus. And so when we come in and take a look, then the work done essentially by the student, indicated by this, reactive normal force, is going to be equal to our, mgy final minus mgy initial, where again, up has to be the positive direction. This is that vertical height on the stairs. And it said it was 8 meters. Okay, like so. And so then when we go in and look, let me put my initial on this one. If you factor out the mg, then you get, y minus y naught. And really, you can claim that y minus y naught is essentially the vertical height. So this is where many people will get, mgh. And I kind of begrudgingly go, yeah, that seems pretty good, that we should use the h here in this instance, okay? And so then to calculate our average power, then what we're going to do is we're going to do the work over the time to get that average power. So the average power would be the work, exerted by the student divided by the time, which is in the form of a reactive normal force. So then this is kind of our mgh over the time, like this. And so a lot of people go, oh, look how simple this is. But to get to the amount of work done being mgh is not really very easy. It involves a bit of, a discussion type of thing. And the other thing that you should note is that if they ran down the stairs, the h is negative. So again, maybe an argument for why the y values are better than the h values. But I think a lot of people do this mgh like this. Okay, so let's calculate our average power. The mass of the student was 70 kilograms. G is again our 9.80. Do not make it negative. The height was our 8 meters. And since we went up, it's positive. And the time was 10 seconds. So what do we get for the average power? $548.8. Thank you. This is in watts. So if we wanted to compare it to like a hair dryer or something like that, I could do a pretty good job. But we should probably go in and do the conversion into horsepower to kind of see where we're at. And we had that 1 horsepower is 746 watts here. So if we take our 548.8 divided by 746, yeah, then we get, what is that, like 3/4 or so? Yeah, 0.74. And that seems about right for how much power we can exert physically. We can do big amounts of power, but only for short amounts of time. And that's one of the things you want to be careful with, is you can hear statements like the petawatt laser in the first floor of the physics building on the UT campus has a higher power output than all of the power plants in the state of Texas combined. You're like, huh? How does that work? Well, I said it was the power, not the energy. So what you get is that in order to generate that super high power for the laser, then they gather the energy in these big capacitor banks on that first floor. and then they dump the energy really fast and get high power output. So it's not that it uses more energy than the plants all make, it's that it does more power. The rate at which we do the energy is greater. So it's really easy to get the energy and the power kind of jumbled up. And so you want to be kind of careful with that. The analogy I like is that, if you're at a semi-primitive campsite, and so you have a little water available, and so, but it's just like a trickle, right? And so like after like the third day, you're like, I gotta wash my hair, I gotta get clean. So how are we going to do this is you take the little trickle of water, you put it into a bucket, gather it up, and then you can dump it over and, clean your hair, clean your body or whatever we need to clean, kind of things, the tent itself, whatnot. So that's kind of the relationship between the energy and the power. The power is the rate, the energy is like the amount of water kind of thing.